Hello, my name is Arash Takshi. I'm an assistant professor at the Electrical Engineering Department, University of South Florida. This short video is about reviewing the concept of voltage divider and reviewing a few circuits related to that, trying to understand that when and how we can use equations to find the output voltage of a voltage divider, or if it is necessary, how to design a voltage divider to get a certain voltage at the output of a circuit. Well, a very simple form of a voltage divider is a circuit that has two resistors in series connected to a power supply. As you can see in the figure, a circuit can be presented like this with two resistors R1 and R2 and a power supply with the value of VCC. So the question is that in such a situation, what's the output voltage or the voltage across one of the resistors? How can we find the voltage across only one of the resistors? So conventionally, if we want to solve the circuit, it is as simple as trying to go for KVL, KCL in this circuit. So as you can see, these two resistors are in series, so the total resistance of the circuit is R1 plus R2, and therefore the current that is passing through these two resistors should be the voltage across these two resistors, VCC, divided by total resistance R1 plus R2. And the third step is to find the voltage across only one of the resistors, let's say R1. So if we know the current is I times R1 should be equal to the voltage across that resistor. And since the current is already calculated as VCC divided by total resistance, so the output voltage, V out, is equal to R1 divided by R1 plus R2 times VCC. What does it mean? Well, it has two significant conclusions on this equation. The first thing is that if we are looking at two resistors in series and applying supply to both of them, and we are taking just voltage across one of them, that voltage should be a fraction of the total voltage. So we get always voltage less than the total voltage VCC. The second is that if you want to quickly find the output of the voltage divider, you don't need to go for the KVL, KCL every time, but instead you can use this quick equation as saying that output voltage is always equal to R1, the resistor which we are looking the voltage across that, divided by R1 plus R2 times VCC as the total voltage. We have to be careful that we cannot use this concept every time, and we need to analyze the situation before applying the equation. Well, although it's very popular to use voltage divider in a the circuit that I showed, but you may find different circuit diagrams in which still the circuit is practically a voltage divider. So for example, as we saw, the circuit in the middle now is the same as the circuit from the previous slide, and it's clearly V out is a fraction of the VCC. But since R1 and R2 are in series, so someone can draw the circuit diagram in a different way to put R2 horizontal, as you can see on the left figure. So practically the figure at the left and the middle are the same, and the same equation to describing output voltage versus the input voltage works in here too. Also, in electronic circuits, we usually simplify the circuit diagram by not showing the loop for the power supply, so we can go for a vertical approach in which R1 and R2 are in series, the figure at the right side of the slide. So we choose a reference for the circuit presented as the ground, and the power supply voltage can be presented with a bar or different symbol at the very top of the R2. So VCC is the voltage supply, the ground is the reference, and of course the output voltage V out would be the node that connects R1 and R2 together. And when we are looking for V out, practically it's the voltage at the this node with respect to the ground as the reference. So choosing a reference node as the ground is very critical, and the ground is usually shown as a G and D with the different symbols. But remember that ground and earth in circuits are different, and the purpose of using ground is basically choosing a node in a circuit as a reference to calculate the voltage of every other node with respect to that reference node, whereas the earth is usually used as a protection for the circuit and has a different concept which is going to be covered in a different video. Anyhow, as you can see, for the right figure, which is the same as the voltage divider, still we can look at the equation for finding the output voltage. So V out is always R1 divided by R1 plus R2 multiplied by VCC as the voltage source. Well, considering that this equation describing the output voltage of a voltage divider, we can see clearly that if the two resistors R1 and R2 are identical in terms of the value, so the output voltage must be half of the total voltage. So R1, when R1 is equal to R2, V out would be VCC half. And also, if R1 is much smaller than R2, then we are expecting that the fraction that we are talking about would be much closer to 0, meaning that the V out is practically almost 0. Whereas if R1 is much greater than R2, the situation would be opposite in a way that the fraction of R1 over R1 plus R2 would be almost equal to 1, meaning that the V out would be almost equal to the VCC. But remember that again, in the voltage divider, resistive voltage divider, output voltage is always less than the supply voltage. So nevertheless, V out cannot exceed VCC. Well, knowing about the voltage divider, we can go for a very simple circuit using a potentiometer to make a voltage divider. How does a potentiometer works? Here we have a picture of a typical potentiometer. You can see that there is a sort of a arrow in the middle of the circle which shows the sliding pin of a potentiometer. A potentiometer is practically as a variable resistor, as shown in the diagram at the right side of the slide, in which we have a constant resistance between the two end pins of the device, and the middle pin is the one that works as a sliding pin, which can move from one end to the other end of the resistor. So when the position of the slider is at the extreme one end, we can assume that it is almost 0% factor for the X in the resistance. So the resistance between the ground and the middle pin would be 0 if X is 0. But by turning the sliding in the middle of the potentiometer, we can change that percentage from 0 to 100%. So and based on that, the resistance, the portion of the resistance between the ground and the sliding output would be different, and to satisfy the condition that the total resistance is always constant, meaning that the resistance between VCC and the output would be always 1 minus X times R. So practically in this circuit, R1 is equal to XR and R2 is 1 minus X times R. Using the voltage divider equation that we had, we can see that the output voltage in such a situation would be equal to XR over XR plus 1 minus X times R times VCC, which after simplification it would be X times VCC. Practically it means that V out can be from 0 volt when X is 0% to VCC when X is 100%. And of course, if we put the the middle pin in the middle of the range, so X would be 50% and V out could be half of the VCC. So we can get anything from 0% to 100% of the VCC by turning this knob or the middle pin and position it in the right percentage. Well, you may find that there are different symbols in the circuit diagrams for presenting ground. So at the left you can see that the ground can be presented as a sort of the lines or a triangle, an upside down triangle, or also VCC or the power source can be presented as a sort of the bar with the label of the VCC, or a circle or an arrow. It doesn't matter. Usually the value of the VCC is described as given in the. Well, remember that this concept, because it came from KVL, KCL in a simple circuit, including two components, can be applied. This concept can be applied on an impedance voltage divider too. In a situation like that, assuming that instead of R1 and R2 we have Z1 and Z2, still V out would be equal to Z1 over Z1 plus Z2 times times of the signal voltage. And remember that if it is a impedance, we need an AC source, and therefore the input or the voltage cannot be the DC. A very obvious example is that if we have two capacitors instead of the two resistors in series, and we want to find out the V out for that, it is as simple as assuming that the impedance of a capacitor is Z1 is 1 over C1j omega, and Z2 is 1 over C2j omega, and therefore putting it in the equation of the V out is Z1 over Z1 plus Z2 times V signal or V source. We get the V out is equal to C2 over C1 plus C2 times V source, meaning that regardless of the frequency of the source, always V out is a fraction of the V source, and that fraction comes from the value of the capacitance, so the ratio of the C2 over C1 plus C2. And so this is a example for voltage divider in an impedance case. And again, remember that for the impedance case, we need to have an AC source instead of the DC. Well, as I mentioned at the beginning of this video, we have to be careful that how we implement the voltage divider equation to analyze the circuit. Sometimes you may find a circuit that a part of the circuit looks like a voltage divider, and that can excite you to quickly calculate the voltage at a certain node, ignoring the rest of the circuit. So remember that we came up with that equation assuming that the current that passes through R2 and R1 are the same. So in a situation which is very common in most of electronics and electric circuit, that if you do have a voltage divider and the output of that circuit is connected to a different load, or load, let's say in this case, the current that passes through R2 is not the same as the current that passes through R1 anymore, because it's going to be split to a current going to the load and the current that goes to R1. Therefore, the application of the voltage divider equation may not be straightforward in case like this. However, we can kind of simplify this circuit to a more practical way of using a voltage divider for analyzing the circuit. The way that we can look at this circuit is that practically R1 and R load are parallel in the circuit. So if we assume that there is an equivalent resistance for R1 parallel to R load, therefore the total circuit now is going to be a voltage divider in which we have R1 parallel to R load divided by R1 parallel to R load plus R2 times VCC would give us the output voltage of the circuit. We reviewed this concept a little bit more in one of the examples at the end of this video. So let's start with a very simple example. Assume that we have a 12-volt power supply and then two resistors, 5 kilo ohms, and we are interested to find the V out. you can do it again by solving KVL KCL, but the purpose of this sort of short videos is to bring it up to the level that you can use your skill to the level that use your engineering analysis skill to guess or calculate the answer before trying to solve the circuit with basic equations. So as we know that if we do have 5 kilo ohm, 5 kilo ohm resistor, there are two identical resistors, so it's a voltage divider that we are trying to divide the voltage to half. Therefore, the output voltage could be 6 volts. If you prefer to solve the circuit by using the equation, it is a circuit, it's a voltage divider. So R1 is 5 kilo ohm, R2 is 5 kilo ohm, therefore V out would be 5 kilo ohm divided by 5k plus 5k times 12 volt as the voltage source. Again, the answer would be 6 volt. Let's go for example 2. In this, we have the same voltage divider, 5 kilo ohm, 5 kilo ohm, but now we are connecting a load resistance to the output of the circuit. There are three different cases that it has been asked to find the output voltage if our load is 500 kilo ohm, or it's 5 ohm, or our load is 5 kilo ohm. So we start from case 1. We understand that if we want to solve the circuit like this, that we need to first figure out what's the equivalent resistance of the 5 kilo ohm in parallel with our load. If we have a 5 kilo ohm resistor and we put a 500 kilo ohm resistor in parallel with that our load is significantly larger than 5 kilo ohm. So when we do the parallel resistance equation for this, we will find out that the equivalent of the total resistance of the 5 kilo in parallel with 5 kilo or 500 kilo ohm is almost the same as the 5 kilo ohm, because the parallel path is significantly larger in terms of resistance than the 5 kilo ohm. Therefore, the equivalent of the R1 parallel R load is almost 5 kilo ohm, and R2 is 5 kilo ohm too, so it is giving us again R1 or equivalent of R1 5 kilo ohm and R2 5 kilo ohm. Obviously the output would be 6 volt as the voltage divider. Well, if we go for the case B, in which our load is 5 ohm, 5 ohm is such a small resistance that kind of make it would be very dominant when we put it in parallel with 5 kilo ohm resistor. So again, 5 kilo ohm resistor in parallel with 5 ohm, this time would give us 5 ohm resistance. And 5 ohm is much smaller than R2. If you recall, we had the rule that if the total resistance of R1 is much smaller than R2, we know that the output is almost 0. You can try to put the numbers into the equation, and then you learn that the 0 volt as the output voltage is quite a reasonable value to be considered as the output of such a circuit. But case C, we are talking about 5 kilo ohm resistor. That 5 kilo ohm resistor is now significant or comparable to R1. We cannot kind of ignore that. So looking at the parallel resistance equations, R1 in parallel with R load would be 5 kilo ohm in parallel with 5 kilo ohm for case C, and therefore R1 R load divided by R1 plus R load would be the equivalent, giving us 2.5 kilo ohm resistance for the equivalent of the R1 R load. Therefore, V out would be equal to 2.5K as the equivalent of the R1 in parallel R load, plus 5K, 2.5K plus 5K would be total resistance times 12 volt. It gives us 4 volt as the output. This example is showing us a very specific thing about a voltage divider. As you can see, if the resistance of the load is significantly larger, as we had it in case A, pretty much the load effect on the voltage divider is negligible, and we get the same voltage, 6 volt at the output, if the R load is much larger than R1. But for case B, we saw that for very small resistance, 5 ohm is a heavy load on the circuit, and it kind of dominates the behavior of the circuit by bringing the voltage to almost zero. And in case C, when our load is 5 kilo ohm, because it's comparable to the R1, the voltage at the output is now less than 6 volt, and it's kind of bringing down the voltage of the voltage divider to a lower value from 6 volt to 4 volt when the output of the circuit is loaded. So the note, the important note on this example is that the effect of the load on a voltage divider is to reduce the output voltage. So in the absence of our load, we had 6 volt. By connecting our load, we always bring the voltage to a lower value. If our load is very large, that change would be kind of insignificant and we still get 6 volt. But if our load is anything comparable to R1, the output voltage would be certainly lower than 6 volt that we used to get before connecting to the load. The last example is a sort of a design question. We want to say that if we have let's say a voltage divider circuit as we had, but this time instead of trying to find the output voltage, assuming that we know that the power supply is 10 volt and we are looking for how to choose one of the resistors or maybe both resistors in a way to get 2 volts out of that. So assuming you have a 10 volt power supply and you need 2 volts voltage for a part of the circuit as a reference or whatsoever, and you're wondering that how you can design the circuit to convert 10 volts to 2 volts. I'm not saying that this application works for every voltage change, but for certain case, if you know that the answer should be done by doing the voltage divider, so we can just simply choose 2 resistors that bring the voltage of the 10 volts to a lower value. Well, of course you can use the voltage divider equation and then putting V out and VCC values into that, and then R2 finding what's the value for R1. But the quick approach is here is that you say we have 10 volts here and we wanted 2 volts here, so it's about pretty much 20% of the VCC that we need at the output. So if here we have 8K, we just need to put a 2K resistor here to kind of get the voltage that we want, because then it will be 2 divided by 2 plus 8, 10 times 10 volt as the output. So how we can find the resistor if we wanted to calculate that as an engineering approach to find how to calculate the R1 value, it is as simple as this, to say that okay, the current that passes through the first resistor I is equal VCC minus V out divided by R2. So 10 volt minus 2 volt divided by 8K would be 1 milliamps current passing through the top resistor. The same current is certainly passing through R1, and we wish to get the 2 volts out of that. So let's say that if we want to get the 2 volts by passing 1 milliamp through a resistor, that the resistance must be equal to 2 kilo. I hope that this short video with 3 examples have helped you to kind of review the concept of the voltage divider, and you can certainly find many different configurations of the circuits that voltage divider can be applied to, and knowing the concept, knowing that how to use the equation, I hope that you can practice on this with more examples and use it as a sort of a skill to analyze different circuits. Thank you very much for watching.